12 through 36. $34. Okay. Yeah, let me start at the beginning so we. All right, you said 12. All right, what about 12? Well, you have to look at the shape. So because it's a point, I know it's absolute value. So the parent graph there would be absolute value of x, right? The parent function, right? That would be your equation. Well, it would be. Okay, you're right in how you're thinking. Because it's flipped, it would be negative in front. But what you're going to do whenever you say negative f of x, it goes in front of the. Why are all the chairs ending up at the front? Well, there's only like 12 of them. I think it's third block. I think it must have been. I don't know. Ugh. This is my parent for that one, right? And it's going down this way. This was 1, 1, negative 1, negative 1. So if I want to do negative f of x because I know that's what's going on, right? To do that, I just throw a negative in front of this. So my equation would be f of x, my new equation, negative absolute value of x. Yes. So the transformation that's happening there is a what? Reflect over x. That's exactly right. Domain. There you go. How about the range? There you go. 0 with a bracket. How about the next page? So that's 15 through 18. 16, sure. All right. 15 and 16. All right, so 15, tell me what's happening. It shifts up 2, right? So it takes every single point that was on the parent, and let's think about the parent for just a second. Here's the parent, right? It takes every single point on the parent and it shifts it up 2. So this one was 0, 0, now it's 0, 2. This one was 1, 1, and now it's 1, 3. This one was negative 1, 1, and now it's negative 1, 3. So everything gets shifted up. Everything gets shifted up by 2. Does that make sense? So the transformation there is, of course, just up 2. What is the domain? Negative infinity to infinity. What's the range? There you go. 2 to infinity. And then you said number 16. So 16 is just a reflection over x. It's just flipped over, right? Because that negative is out front. So my parent function here is x squared. The transformation is reflect over x. And let's graph it. Okay. It's just going to flip over like that. Domain, of course, negative infinity to infinity, and range, negative infinity. What else? Yes. Flip on over to 25. We get into our dilations. All right. Here's the thing with dilations, and this I helped several of you on Wednesday with some of these. Writing the equation to me can be difficult, so we have to figure out exactly what's going on. This is where I can't remember what color sheet I ran y'all this time. What was it, green? This is where your green sheet will really help you too. So what I'm going to look at here, I'm looking for a place where either the x coordinate is 1 or the y coordinate is 1. Okay, so either where x is 1 or y is 1, so I can tell exactly what's happening, right? Are y'all with me there? I think I'll choose when x is 1. I didn't know I could write on here. Oh, well, I'll just do this. This is quite convenient. So I'm going to pick here. This looks like a pretty good point, right? So the coordinates of this point would be 1, 3. Do we all agree? Now, if that's 1, 3, think about what the parent looked like. And let me just put the parent on here so you see. 1, 1, negative 1, 1. That was the parent, right? And now it looks like it's come in some. So the question is that a horizontal or a vertical dilation? It could be either. How am I going to decide which one I'm going to use? Well, I'm going to look at the point. If I go from 1, 1 to 1, 3, what's changing, the x or the y? The y, right? So since the y is the one changing, the y is the vertical axis, I'm going to call this a vertical. And now looking at it, is it a shrink or a stretch? Does it stretch out this way or shrink it? Stretch, vertical stretch, right? I found one that had either a 1 for a y coordinate or an x coordinate so that I could compare it to the original parent graph of 1, 1. So I'd say this is a vertical stretch of 3. Yeah. A vertical shrink? A vertical, yep, yep. So you wrote the equation. Well, that's fine for like writing the equation whenever you have to come here and write the equation, but the question here is what's the transformation. So if you could then look at the equation and tell that it was a vertical stretch, then that's fine. Yeah, that's fine. We'll keep going and it might make some sense. Yeah. Yeah. Let me finish this one. All right, does that make sense? So on your little green sheet, it says that vertical stretches or shrinks, right? I take x, y, I leave x alone, and I multiply y by whatever that factor is. That's how I came up with that factor. Look at 24. Again, I'm looking for a point where x is 1 or y is 1, and it's an even, it crosses over at a nice clean point for me. So look at this one. This point looks like 1, 2, 3, 1. So I'm thinking this might be a what? Horizontal stretch, right? That's what it looks like. It looks like a horizontal, and I need to go back to that other one and write the equation. What? This is a horizontal stretch of what? Well, remember I have to flip it. In the equation, it'll be 1 over 3, but it's a horizontal stretch of 3. So whenever I write the equation, it's going to look like this. Remember, everything horizontal is opposite. So your A is 1/3, but yet it's a stretch of 3 because it flips over. Does that make sense? You remember doing that? Everything's opposite with horizontal. Over here, this equation would be absolute value of x, but the 3 goes out here because it's vertical. Does that make sense? How about this? Yeah. Verticals go outside, horizontals go inside. Horizontal inside and opposite, vertical is outside and same. So if the y is the one that's changing, it's vertical. If the x is the one changing, it's horizontal. Yeah. It could be, that could be a vertical shrink or a horizontal stretch. You can write it either way, but what you want to do whenever you look for a point like this, it'll kind of clue you in on which one you need to use. You're looking for a place where x equals 1 or y equals 1, a point. Just so you have a point of reference is what you're doing. Yes. No, if x is changing, it's horizontal. If y is changing, it's vertical. Yeah. Well, so I could describe them. I could describe a horizontal stretch the same as a vertical shrink. Like I could use them interchangeably. But whenever I'm given a graph to look at, the easiest thing to do is finding that point that has one coordinate of 1, like either the x or the y to be 1, and then seeing which one changed as to if I should describe it as vertical or horizontal. So look at the one right before it. What point would you use on here to describe the shrink or stretch? That's exactly what I would use. So if I go from 1, 1 to 1, 5, what's changing there? The x or the y? The y. So I would call it vertical. I know that it's stretching because it's getting skinnier, so a vertical stretch of 5. And again, vertical just goes outside and stays the same. So f of x equals 5 times the absolute value of x. Yeah. I would, with the parent function, write there a. So your parent function is just f of x equals the absolute value of x. Your final equation is going to be f of x equals 5 times the absolute value of x. So then when will we use like the a times? Well, so you are doing that. Let me see if I can explain this a little better because I think that's where you. Okay, if I said. Change f of x to be negative f of x. Right? Then that would say whatever f of x was, I look at what f of x was to start with. Let's say f of x was the absolute value of, I don't know, 3x. Then to make it negative f of x would be, put a negative in front of that. It's just telling you to put a negative in front of the whole thing is what this is saying to do. It's just kind of a general form. What else? 26. Okay, so here you can't find one that's, so maybe I need to, you're saying this is 2, 2. Maybe on this one I can do both, or yes. I would say 1, 1 becomes 2, 2. And there's an easier way to do this that we'll talk about whenever we get to some multiple transformations here. But for right now, I would say this is a horizontal shrink. Good. Yeah, hold on, hold on. A X Y becomes, flip it here, which means it's already flipped here. Yes, so this will be a stretch. Sorry. But they're not negating each other. Even though a horizontal stretch is the same thing as a vertical shrink, these should essentially be negating each other, but they're not because of the squared. So what I would do here is I would say this is 2. Did anyone get, it doesn't make sense. That's the same thing. You could write it that way. Yes. You're just different values that, yeah, yeah. Either one of these would be okay. This or this would be, yes. Vertical is what it is. Horizontal's the opposite. If I do it as a, if I label both of them, it would have to be a horizontal stretch and a vertical stretch. But if I put them together, so it could be this, or it could be a vertical shrink of a half. In other words, on this particular function, a horizontal stretch of 2 combined with a vertical stretch of 2 equals a vertical shrink of a half. That one was tough. You could also look at this the way we did it before, and I'm sure several of you probably did this, and you're probably looking at it going, what in the world are they talking about? It wasn't even that hard. If you go from 0, 0 to 2, 2, you went up to, oh no, that doesn't give you your first point, does it? Never mind. Never mind. Scratch that. Yes. Yes. Give me another one. 27. Yes. 27. Is it another one like that? Only I think on this one, I would use, no, undo one. Let's see. Where'd it go? What number was that? Oh, no, this one's not like that. There's a point. What point is that? Come on, y'all can do this. 1, 3. So what's changing, X or Y? Y. So I'm going to call it vertical. Vertical, it is what it is. That makes it a little bit easier. So it's a vertical stretch of what? Of 3. That's right. So look at this. I started with 1, 1. It became 1, 3. The x stayed the same. The y is what changed. Yes. I don't remember which one it was, but it was when all of them were 24. It went from, yeah, from 1, 1 to 3, 1. Vertical stretch of 3. So okay, so from the vertex, right, I went, or actually from the parent function of 1, 1, it became 1, 3. So what changed was the y, and it changed by a multiple of 3. Bigger than 1 is a stretch, less than 1 is a shrink. So that 3 just goes outside, and I wrote everything else. What? Vertical, yes. Vertical, bigger than 1 is stretch, less than 1 is shrink. And horizontal is opposite. So for horizontal, greater than 1 is a shrink, less than 1 is a stretch. That's on your little green sheet too. Yeah. Mm-hmm. Which 29, the first one or the second one? Ooh. Okay, here's where you're going to really need your little green sheet, okay? Your green sheet's going to help you immensely. First thing I want to do, well, obviously parent function, we know absolute value of x, right? What transformations are happening? Let's identify them first. It's outside, right? It's outside, so it's vertical. Is it a shrink or a stretch? Shrink of 1/5. Y'all all okay there? Okay. Now look at your little cheat codes in the far right column of your green sheet. For a vertical shrink, it says you take xy and it becomes what? X, AY. Well, what's that saying? Your A, this A is this number. Okay, so it says take every X, keep it the same. So remember what points I'm working with to start with on the parent. I'm starting with 0, 0, 1, 1, and negative 1, 1. Keep X the same, but multiply every Y by A. Okay, so keep X the same. Now multiply the Y by A. What do you get? 0 times 1/5. 0. Keep X the same. Multiply the Y by 1/5. 1 1/5. Keep X the same. Multiply the Y by 1/5. You multiply the Y by this number in front. So now, oh, why is that moving? All right, so I've still got 0, 0. And then I got 1/1/5, and you don't have to worry about being extra super precise here, but just 1/1/5 up a little bit, and I'm just going to connect. It should be stretched out because it's a vertical shrink, which makes it wider. Right, because of the way that it gave it to us. Yeah. Say that again. Yes, it would be. For this one, it would be. It wasn't like that with the squared because you had to square it first. That's why they didn't absolutely negate each other the way it was, but yes. Yes. What do you think's happening with 30? What kind of shrink? Vertical. How do you know it's vertical? It's outside. That's exactly right. This is horizontal. Just to show you the difference. Because these get kind of confusing when you got just the squared or the absolute value. So that's the difference between outside and inside. And then same thing, my same starting points, my 0, 0, 1, 1, and negative 1, 1 become, multiply each y by 1/3. So 0, 0, 1, 1/3, negative 1. It's going to look very similar to the other one, just stretched not quite as far. But it's hard to tell on these little graphs. Of course, you could do the up 1/3 also. Yeah. Yes. 28. Parent function, of course, is absolute value of x. Vertical or horizontal? How do you know? Numbers on the outside, it's vertical. Shrink or stretch? Stretch, that's right. Of what? 3. Again, because it's vertical, I take every point and I multiply every y. I leave x alone and I multiply every y by that number that's in front. So 0, 0 becomes 0, 0 still, but what does 1, 1 become? 1, 3. And how about negative 1, 1? Negative 1. So dividing by fraction or multiplied by the flip, either one of those is the same. I would probably multiply by the reciprocal, be a little easier. Yeah, that's vertical. 34. Yes. I don't have like the original one here. Am I like might have colors? Oh, sure. Yeah, yeah, absolutely. And I show you these this way, even though with these basic parent functions, it's probably easier to graph them from the slope part of it, like just saying, oh, well, I know this is up 1/3 for the very first point. But some of the parent functions that we're fixing to get into, you won't be able to do that on that first point, so it makes it a little harder. All right, let's parent function here is just x squared. Vertical or horizontal? How do you know? It's inside. So I know I'm horizontal. Is it a shrink or a stretch? How do you know? It's less than 1. So it's a horizontal stretch is opposite. So it's a stretch, horizontal stretch of 3. Now, if you look at your little cheat sheet, it says that for horizontal, I take xy, x gets divided by a, and y stays the same. But this is where we were saying, really, do I want to divide every x by a third? No. What I'd really rather do is multiply every x by 3. So multiply by the reciprocal. All right. So instead of dividing, it's the same thing though, right? So 0, 0, of course, stays 0, 0. 1, 1, if I do 1 divided by 1/3, that's the same thing as 1 times 3, which is just 3, and the y stays the same. And again, with negative 1, 1, it's going to become negative 3. And if I, yeah, go ahead. 1, 1 became, so I took the x and divided by the a. But if I do 1 divided by 1/3, that's the same thing as multiplying by the reciprocal.
Now, how will we know the parent function just by looking at it?
So you know those 7 or 6 parent functions I told you to be able to recognize? You'll look for whatever's happening, yeah, on that sheet. It'll be one of those. Right now we're just focusing on absolute value and quadratic because it's a little easier to learn the transformations on.
So like on the absolute, so if that has like the absolute value like that,
In it, then that's the parent. Yep. Yep. Yeah. 31. All right, 31. Parent function, of course, absolute value. Vertical or horizontal? How do you know? It's inside. So I've got a horizontal. Is it a shrink or a stretch? A shrink of 1/3. Everything horizontal is opposite. So it flips. So now what's going to happen is every point here, and maybe it'll be easier for you to see it like this, is going to be 1/3 x, and then y is going to stay the same. So I'm going to have 0, 0, 1/3 1, and negative 1/3 1. Does that make sense? Which other one did you say? 36? 32. So same thing here, only this is quadratic. Again, it's horizontal, but it's going to be a shrink because it's the opposite. And it's going to be a shrink of a half. So it's going to be, all of my points are going to become 1/2 x, but the y is going to stay the same. So 0, 0, 1/2 1, and negative 1. All right, let's take a break for just a second because it's not right. Okay. Multiple transformations, whenever we have more than one thing going on at a time and we have to identify what's happening, how do we know the order that we do it and what do we do given just the graph? So here's what I'm going to tell you to look for first. Look for your stretches and shrinks first. Okay, and I've already shown you how you do that, but for this, the easiest thing that you're probably going to do as you look at these is you're going to kind of look for your, even though this is not what we did whenever we were doing them individually, but as they shift, it's a little bit harder to tell. Look for your slope from the vertex to the first point you can find. Okay, so I'm going to walk through this first one with you on your packet so that you can see exactly what I'm talking about. Oh, sorry. I'll give you a chance to copy that because I had some of it already written. Yeah, to the first point you can find on the graph. This is just going to force me kind of to call them all a vertical instead of a horizontal, and that's okay for right now. Do what? Looking for the slope because that'll just go in front. But remember, every vertical stretch is the same thing as a horizontal shrink, and every vertical shrink is the same thing as a horizontal stretch. So I can describe them all. So I'll just be describing them all as vertical as I'm writing this. It's just easier that way as I'm doing multiple ones. What? Point. PT point. Yay. Okay. So let's look at number 37 here. How much can I zoom in? What do I mean by looking for the slope? If I go from the vertex, here's the vertex, right? It looks like the next point that's an actual even point on that I can identify is this one. Do you agree? This is the 37. To get there, what's the slope essentially that I would use to get there? Up 2 over 1, right? Everybody agree? 37. Up 2 over 1. So I'm going to say that's kind of a slope of 2. Instead of calling it a slope, I'm going to say that it's got a vertical stretch of 2. Y'all okay there? Okay. From there, I'm going to look for any reflections. And in this case, I don't have any, right? I'm still just up. And then the last thing I'm going to do is I'm going to look for slides or translations. And those are easy to insert in that equation. So I'm going to give you kind of a general form here, and you've really already done this for both of these. The A here is, of course, my vertical shrink or stretch. What does H do? Left to right. That's exactly right. But it's opposite sign, remember? It does the opposite. That's here and here. And what does the K do? Up and down. That's exactly right. So 3 things I'm looking for. Well, I guess that's kind of, yeah. Stretches, shrinks, reflections, and then I look at the slides last. They're what I'll deal with last. So going back to that number 37. Yeah. No reflections, we said, right? We're good on reflections. I know it's got a vertical stretch of 2. What else has happened here? What other transformations happened from the parent graph? Down 6. We know it went down 6. What else happened? Left how many? Now I just need to plug into the equation, right? My A is going to be 2. So what does this equation look like? F of x equals 2's on the outside because it's vertical, right? My parent function is x squared. How do I say left 3? Is it plus 3 or minus 3? Plus 3 because it's opposite. How do I say down 6? Does that make sense? 2 is coming from that little slope, and the 3 and the 6 are coming from my slides. That's the hardest part about the multiple, is writing the equation. X squared. It's a parabola. It's easier that way when you're writing the equation. Okay. Okay. Yes. All 3 of these are your transformation. It just means I'm doing multiple things to one parabola. Yeah, that's all it means. Look at the range. The range is the y, not the x. So what's the range there? What's the lowest it goes? There you go. -6 up to infinity. Let's switch it up a little bit. Look at number 40. Yeah, let's look at a harder one than 40. Let's do one that's got everything. Well, they don't get much harder than that. Let's do 45. What's the parent function? Perfect. Tell me the transformations that are occurring here. I heard reflection over X. I heard up 6. What else? Okay, these we're going to do, we can do horizontal or vertical. The only time we're only going to do vertical is whenever we're writing the equation given a graph. But these, we can describe them as horizontal or vertical. Horizontal shrink of what? 1/3. That's exactly right. Say it again if you had. That would be a vertical stretch. Yep. Right. Yep. Yep. All right, so let's graph it because it can get confusing on what you do first. Always do your shrinks or stretches first, and then everything else will follow for you. Okay. Follow that same 3 steps: shrink, stretch, reflect, slide. Okay. So let's shrink or stretch. This is where your colored pencils might come in handy because you can see exactly what's going on, but you definitely do not have to. I'm going to graph here. I'm just going to do the parent so you see what's happening. You don't need all of these on here if you can do it without. All right, first thing I'm going to do is my shrink or stretch, and it says it's a horizontal shrink of 1/3. So 0, 0, I go 1/3 1, which would mean 2/3 2, which would mean 1/3 1. So it's going to do something like this. It doesn't have to be exact. You can go up 1/3 if you, yeah. Or actually, this would be up 3/1 because you have to do the, yeah, the opposite. All right, now I'm going to reflect. So now I take all these points that were here and I flip them over the x-axis. So 0, 0 stays. This comes down and this comes down. Sure. Yeah. And now I slide. And where am I sliding? I'm sliding up 6. Is that it? Just up 6. So now I take the red one and I go up 6 on every single point. So the green would be my final. I used to make you draw every single one of them so I could see that you understood the transformations. I'm not going to make you do every single one of them. I just want you to be able to get there and understand the transformations that got you there. Because these transformations would work with anything. If I literally had, if this is kind of what your project's going to get to. Let's say I had I don't know, a smiley face that I was trying to transform. These transformations would work the same with that, sliding, stretching, shrinking, and all of that. So it's important you understand those rules that go along with that. Okay, is everybody okay to finish that packet now? You think you can make an attempt at that? We'll talk about it tomorrow, see how that goes. Let me now talk about your project. Give me your laptop because I need to show you some things there. I told you this was loaded today, and I apologize ahead of time, but I won't need to stand up in front of you and talk this much anymore this week. What? Why did you not plug it in? I did. I just did it in my head. That's why I went. That's why I went to 1/3 1, but it's horizontal, so it's opposite. Great day that following. That's over, yeah, over y. You won't have one of those because it'd be the same thing. Because you do reflections before you slide. So if I have a parabola and I reflect it over over y, it's already symmetrical over y. It would be the same thing. What's the absolute value of negative x? Well, the absolute value of a negative number. Yeah. Same with squared, yeah. Because it would go up 3 over 1. Up 1, 2, 3 over 1. You're getting the opposites mixed up. Flip it to find the point to multiply by your x. So right, so x over a would be x over 3. So 1, 1 would become 1/3 1. Yes, it is. 1/3 happens here up to 1 right here on the yellow. I just kept going and I said, yeah, so that I could get a nice even point. Do I? No, you can just stick them on that desk behind you or beside you and I'll grab them and go from there. All right, here's your project. You're going to use Desmos to help you, and that's going to be the key. I used to do this project without Desmos, and it took forever, and it was so aggravating. But Desmos really makes it easy. But I will tell you, because I let you use Desmos, I am very, very strict on it being your own original design. I've done this for so long that I can always tell if you copy something from somewhere or anything like that. So be very careful. Make sure you are original in what you're doing and you're not just going through and finding something that's already been done. So here's what you're going to do. You're going to make a picture using your parent functions, okay? The parent functions that we've talked about, there's 6 of them in the packet that are up for grabs. Those are the only ones I want you to use. I don't want you to go any further than that. You may not be able to get the shape you exactly want using those functions, but it is okay. You will open up your computer and go to Desmos. And we're just going to do the graphing calculator on Desmos. So just click graphing calculator. And I'm going to show you how we're going to go through some of these. So what we're going to do, the basis of this, is thinking about transforming some of the graphs that we've been doing. For instance, let's say I have, what does this look like? Reflected, so it's an upside down parabola that's just been slid up to, right? Everybody agree it looks something like this, okay? What I'm going to do is I'm going to use graphs like this to create a picture or a drawing, okay? So what I'm going to do is cut a portion of this off. So let's say for my picture I'm doing, I don't know, maybe I'm doing a oval, some type of oval or some type of shape that I need it to cut off here, okay? So maybe I want my restrictions, I'm gonna set up domain restrictions so that it cuts off that part of the graph. So maybe I say I want x to be between -1 and 1. And so on my picture, I would only have this part of the graph. And then maybe I come in and I'm going to show you how to do it on Desmos. Then maybe I want something that, for whatever reason, and this is where you'll really have to start playing around. Maybe I want something that comes around and does this, but I want it to stop right here. And as I play, that looks like a square root graph that's been reflected. Remember, a square root looks like this. And if I reflect it, it looks this way. And maybe I cut it off, and I only want it when x is smaller than maybe 5. So that whenever I graph, it only gives me this part. So now I've got this little piece and this little piece. And together, I can start putting some things together to make some pictures. So, like for instance, if you look behind you, there's a penguin on the lawn. Only those 6 square functions she was able to, if you start looking at them, you'll see different functions that are in here. Linear functions are fine. It's a line, right? It's a parabola. You've got 2 parabolas making the belly. She's got an absolute value there for the nose. The horizontal and vertical lines. You see what I'm saying? These are square root graphs that have been cut off. So she shifted them, stretched them, shrunk them, shifted them, and then cut them off wherever she wanted until she was able to put everything together. So the point is that when you're done, you'll have a list of, and I have several other examples I'll show you. You'll have a list of functions that you can give me, and I should be able to graph your functions and come up with the exact same picture that you have. Okay?
What if you don't?
No, I'm just kidding. You should. And that's why you're going to use Desmos to make sure you do. So let me show you on Desmos how we're going to do this. And I'm just going to do this exact same, I'm going to show you how to do it. And you've played around with Desmos because we did the little activity in Desmos. So let's say I want negative x squared. What did I say, plus 6? I don't remember what I said. Plus 2. Then I want to say, I think I do comma. I have to remember how to do this now. Boo. Okay, hold on, because I have to remember where to trick here to this one. So, for instance, if I wanted that same x squared, actually it was negative, wasn't it? Negative x squared plus 2. And now what I want to do, I think I have. There we go. The squiggly brackets there. Does everybody see what I did to restrict it here? So I said I want that piece of a parabola, but I only want it to go between -1 and 1. And then maybe for my next equation, I want a line. I want 2x plus 3. But I want it to go on forever bigger than -1. So maybe I say, this is getting ridiculous. So maybe I do 2x plus 3, and maybe I want it to be only when I do the curly bracket, x is bigger than, yeah, take your stuff. I'm sorry she said that. Bigger than -2. Or bigger than -1. And then I've got that piece of a line. Do you see how I'm doing this to draw the picture to make the picture show? All right, so requirements. If you take a look at your packet. All right, so we talked about the sketch on here, and then you'll have a full-size picture. Yeah. Hold shift, and then the the little bracket. You see look at enter, the enter button, look up and to the left. All right, so sketch plus final project, and I'll try to cut some of these out so y'all can really see some good examples because I only laminated the really good ones. Those are pretty good. I'm not sure that they're all completely right, but they look pretty and they made decent grades on them, or I wouldn't have kept them like that. You can just set them on the table behind you, and I'll grab them. Make sure you don't Google a picture and use that, and that it's your own picture. Okay. Well, I mean, you can do a reference or something, yeah, but don't look up function transformation graphs and things like that because you'll be able to find them if you do. All right. You have to use at least the parent function's linear, quadratic, and absolute value, but you can use any of the ones on the sheet that I gave you. Some of them have different shapes, so look at the shapes because it may help them. It may help you decide. A minimum of 20 transform functions must be used. Okay? Every function, no parent graphs, everything has to have something, whether it's a stretch, a shrink, a shift, a reflection, something. I'm just going down these bullets, guys. Your design, meaning your picture, and this is where people always lose points, okay? Make sure at least one time you have a vertical stretch. At least one time you have a vertical shift. At least one time you have a reflection. All of those you must occur at least. They don't have to all occur in the same equation, but they must all occur at least one time. We talked about original, neat, and legible. Each function listed on the attached function sheet along with the parent function domain restrictions must be listed. So you're going to list them out. If you need an extra sheet, you most definitely may get one. There are bonus point opportunities if you go above and beyond on this. So if you need an extra sheet to print out, just let me know. Let's see. Oh, make sure each, and this is one thing that everybody in that one didn't do as well as these. That's why we'll try to look at these. Every equation needs to be labeled with a number so that I can see which equation it corresponds to. In other words, she's got number 20 listed here as an absolute value. So if I look on her function sheet list, number 20 should be an absolute value with the appropriate domain restriction. So you really want to label each one to make sure. Now, how will I grade it? If you flip over, here is a little rubric on the back. It makes it very easy for me to grade, easy for me to transform your grade into your major grade that you'll get based on what you have. So if you want to look to see how that's done, there's your rubric. Friday. We'll do Friday at the end of class. That way, if you need to wrap up a couple things in class, you can do that, coloring and things like that. I'll have colored pencils and crayons available for you for the rest of the week. I'll bring them in, rulers and things like that, anything else that you might need. It's got to be done by hand, though. You can't print something off Desmos, so be careful with that. Yeah. Try to get the graph to match it. All right. Any other questions? Yeah. Okay. Any other questions about the